Hello everyone and welcome to my session. Today I'm going to show you how we can build a system that can enable us to develop a real-time fraud detection at scale. To achieve this, we are going to make use of two powerful approaches. One is a traditional machine learning approach and the other one is an agentic AI approach. And to power this entire system, we will use an architectural pattern called event sourcing. So now if event sourcing is something new to you, don't worry. We will explore it later in the session. But before we get there, we first need to understand the database that powers this entire system. And that is going to be Azure Cosmos DB. Cosmos DB makes implementing event source system so simple and straightforward. So let's start by understanding Azure Cosmos DB. There are few key reasons why a developer choose Cosmos DB over other relational databases. The first reason is that it is a NoSQL database. Unlike traditional relational databases where data is stored in tables, rows, and rigid schemas, NoSQL databases store the data as a flexible JSON document. This gives developer much more flexibility. It allows us to evolve the data models easily, store them hierarchically, and handle rapidly changing application requirements over the period of time without worrying about the constant schema migration. The second capability is that it is globally distributed. And this is where Cosmos DB becomes really powerful. If you look at this diagram, each of these black dots represents a data center in different regions of the world. With Cosmos DB, your data can be replicated automatically across multiple regions. And what this means is that user accessing your application from different parts of the world can read and write data to the nearest region, resulting in very low latency. At the same time, this system also maintains high availability and resilience. The third capability is the scalability. Cosmos DB is designed to scale horizontally. Instead of relying on a single machine, data is automatically partitioned and distributed across many machines. This allows system to handle massive data set, very high throughput, and workloads that can scale up to millions of requests per second. Now, if you have attended any Cosmos DB talk or a meetup or a conference, you would have probably heard the statement, choose your partition key wisely. And yes, that advice is absolutely correct. But the real question is, how do we actually choose a good partition key? What really helped me understand partition key design was looking at what's happening behind the scenes inside the Cosmos DB. Because once we understand the internal architecture, choosing a good partition key would be making much more sense to you. So before we go further, let's take a quick look at what Cosmos DB looks under the hood. And this is how it looks. As we discussed earlier, Cosmos DB allows us to replicate our data across different regions. For example, I'm going to take Asia region in this diagram. And within that region, you will be having multiple data centers, DC1, DC2, and DC3. Each of these data centers can span across multiple availability zones. Now, the availability zones are nothing but physically separate locations that has its own power, network, and other components, right? And if you zoom in further, each of these data centers can have multiple machines. In reality, it could be hundreds and thousands of machines within a particular data center. And each of those machines will be arranged in a rack and it will be in a different fault domain. And inside those different machines, we will be having replicas. For simplicity, I have shown here two replicas, but in reality, it could be hundreds and thousands of replicas. And obviously, all these machines do have a storage device and it is clustered together, right? And another important concept that you need to understand is the replica set. If you consider here, RS1 is one of those replica set and it is spanning across multiple machines, across multiple data centers, across multiple availability zones. So if you take a replica set as one entity, this forms a single physical partition. And that goes same with other regions as well. The same concept, you will be having multiple replicas and you will be having multiple copies of your data across those different replicas. And within each of these different replica sets or a single physical partition, you could have one master node followed by other followers node. So when a write request is going to come to the Cosmos DB, it is going to be handled by the master node, and it is going to append the change to its own transaction log or write ahead log, and the data is going to be replicated to the followers. And the write is going to be committed only after majority of those replica is going to acknowledge that particular write. And this acknowledgement is called the quorum, right? So for you to form this majority quorum, so for example, like we have 5 replicas, and for us to form this majority quorum, we should have at least 3 machines up and running, so we can handle 2 machine failures. And in that case, the write is going to be committed. If there is going to be 3 machine is going to be down, during that time the write operation is going to fail. So far, what we have seen is a replication within a single region, but Cosmos DB allows us to do more than that: multi-region writes. This means application from different regions can write to the database at the same moment, right? Imagine two users interacting with the system from different parts of the world simultaneously. Both region may attempt to write to the same data partition. And when this happens, Cosmos DB record these writes as tentative writes and replicate them across regions. And it resolves the conflicts using different strategies like lost writer wins or custom conflict strategies. And once it is resolved, the final state is propagated to all those different regions and eventually converges to the same state everywhere. Now we finally come to the concept of logical partition. So far, we have seen how complex the internals of Azure Cosmos DB actually are, right? We looked at the machines, replica sets, leaders, followers, replication, and physical partition. And this is exactly the reason why Cosmos DB introduces the concept called logical partitions. As a developer, we really don't need to worry about all those complexities. We don't need to think about how data is replicated, how it is sharded across machines, or how partitions are managed internally. All Cosmos DB asks us to do is choose a good partition key. The goal of the partition key is simple. It is to help them to distribute the data across all the partitions in the system. Now let's see what actually happens once we choose a partition key. Cosmos DB maintains something called as a full hash base, which ranges from 0 all the way to maximum value. So whenever we insert a data, the value of the partition key is sent through a hash function, and the result is mapped somewhere into the hash base. Cosmos DB then divides that hash space into ranges. It is called as partition key range or feed range. For example, we might be having 0 to 20, 21 to 30, 31 to 40, and so on. Each of these range maps to a physical partition. So if a partition key value hashes into 0 to 20 range, that data will be stored into physical partition P1. If it hashes to 21 to 30, it might go to P2, and so on. And each of these physical partition is backed by a replica set of the machine, which we have seen earlier. So this hashing mechanism is what allows Cosmos DB to automatically distribute data across the cluster. If too many requests ends up using the same partition key value, all the traffic will go to the same logical partition in turn, which maps to one physical partition. And this is what led to something called as hot partition. Now, if this is something that you end up with, meaning you have created a hot partition because of poorly chosen partition key, there aren't many options. In most of the cases, you have two ways to solve this. One is to have or perform a container copy job. Essentially, you create a new container with a better partition key, then migrate the data to that container. The second option is to use change feed. You can run a process that reads the change feed from the existing container and writes them to the new container with a different partition key. Once the migration is complete, you can decide how you want to use these containers. Sometimes you could keep both of those containers so that like you can serve one part of the queries with one container and the different queries with other containers. But recently, I think Microsoft also introduced global secondary index capability, which is in preview, that allows you to perform the same, but more simpler way. But ideally, we don't want to end up in the situation in the first place, right? So the real question is, how do we choose a good partition key from the start? One common guideline is to choose high cardinality. High cardinality simply means that partition key has many possible values, which helps to distribute the data across many partitions. For example, something like customer ID typically has high cardinality. But if you just focus on high cardinality to solve all the problems, then again you might end up in this same issue. For instance, you might think time would be a good partition key, but because it produces different values. But imagine an IoT scenario, right? Thousands of devices is gonna send the telemetry at the same time. So which means that the write absence happens at the same time, and they all end up targeting a single physical partition. And that again leads us to have a same hard partition key problem. So instead of thinking only about the cardinality, we need to think about how traffic should be distributed. A good partition key should help distribute write traffic, read traffic, and also the storage volume, because there are also storage limits per partition, which we will see in a bit. So there are different partition key strategies that you could follow. One approach is using a synthetic partition key, where we combine multiple attributes together. This helps to distribute the data. And the other another approach is to use hierarchical key. This allows you to define multiple levels of partitioning, up to 3 levels. This gives the system more flexibility how it distributes and queries the data, and helps avoid the same limitations, right? So the key takeaway here is that partition key design directly impacts scalability. Now that we have understood how data is distributed, let's see what actually happens when our application send a request to Cosmos DB. When a request arrives, it first reaches the replica set that owns the partition containing the data. Within the replica set, one of the follower replica typically handles the read request, while the leader replica primarily focus on the write operations. This operation helps to reduce the load on the leader node and improves the overall system throughput. Once the request reaches a replica, it is forwarded to a database engine. Inside the database engine, the request goes through several stages. First, the query processor passes the query and builds the query execution plan. Then the request moves to index manager, where the Cosmos DB performs an index lookup to identify which documents match the query. Finally, the request reaches to the storage engine, which retrieves the actual data from the disk, and the result is returned back to the client. Now let's compare this to the point read operation. A point read happens when we already know two things. One, the ID of the document. The other one is the partition key value. When we have both of these values, we can use Cosmos DB SDK to perform point read. In this case, Cosmos DB does not need to parse a query or generate a query plan. The request goes directly to the replica set, and inside the database engine, it performs a direct key lookup, and from there, storage engine retrieves the document immediately, because we skip the query processing and the planning step. The operation becomes now much faster and more efficient. This is going to result in lower latency and lower cost. In Cosmos DB, every operation consumes something called as request units, and request units represents the cost of an operation in terms of CPU, memory, and IOPS. So whenever possible, try to design your application in a way that allows you to perform point reads instead of queries. This is going to significantly reduce the latency and the RU consumption. Now, let's talk about some important limitations you should be aware of when working with Azure Cosmos DB. These limits are not necessarily bad. They actually exist to help Cosmos DB maintain performance and scalability. But as a developer, we need to design our systems with these in mind. The first limit is related to physical partition. A single physical partition can store up to 50 GB of data. Once that limit is reached, Cosmos DB will automatically split the partition and distribute the data across multiple physical partitions. This process is handled automatically by the platform, so developers don't need to manually manage sharding. However, there is another limit that is much more important from a design perspective. A logical partition can store up to 20 GB of data. Unlike physical partitions, logical partitions cannot be split automatically. So, if a single partition key value grows beyond 20 GB of data, you may start seeing errors like throttling error. This is another reason why choosing a right partition key is so important. You need a key that distributes the data and as well the traffic across multiple partitions. And this is where the approaches like synthetic keys and hierarchical partition key can help. The next limit is related to the throughput. Each physical partition can support up to 10,000 request units per second. What this means is that if a large amount of traffic targets the same logical partition, all those requests will be handled by the same physical partition in turn. And that again leads to hot partition scenario as we seen earlier, where the system becomes throttled even though other partitions are idle. Another limit to be aware of is the document size. In Cosmos DB, size of a JSON document is maximum size of a JSON document is 2 MB. In most application, it is quite difficult to reach this limit, but if the documents are poorly designed, then it might be possible. Earlier, we discussed that point read are actually efficient than the queries, but there is one exception. If your documents become very large, for example, close to 1 MB or 2 MB, a point read might actually consume more request units than a query. So the document size plays a vital role. And the final limitation to keep in the mind is related to transactions. In Cosmos DB, transactions are scoped to a single logical partition. This means atomic operations such as transactional batch operations can only be performed within the same partition key value. Cross partition transactions are not supported in the same way as we do in the traditional relational databases. So, understanding these limits helps us design our system in a way that fully leverages the Cosmos DB's distributed architecture while avoiding common pitfalls. Now we are almost ready to talk about event sourcing. But before we get there, I want to show you something interesting. Because if you look closely, a very similar pattern already exists inside Cosmos DB itself. And that pattern is called change field. Earlier, we discussed how data is distributed across logical partitions, how partition keys are hashed, and how those hash ranges map to a particular physical partition. Inside each physical partition, we have a replica set of machines, a leader, and follower replicas. Whenever a write happens, the leader replica first appends the change to its transaction log, or you can call it as write ahead log, and those changes are then exposed as a stream called change feed. You can think of change feed as a continuous stream of all the changes happening in the database. Every insert, update becomes part of the stream. And because Cosmos DB is partition, each logical partition produces its own ordered stream of changes. Now, from this change feed stream, we can have multiple workers processing those changes. Each worker is responsible for processing specific range of partitions. To coordinate this work, worker uses something called as a lease container. This lease container stores a metadata such as like which worker owns a particular feed range, the continuation token, and processing checkpoint. This means that like if one worker is gonna fail, another worker is gonna take over and resume the processing from where the previous worker stopped. All of this coordination is handled by a library called change feed processor. It automatically distributes the work across multiple workers and ensure the system scales as the workload grows. And if you think about it for a moment, what we actually get here looks very similar to an event store because every change to the system is recorded as an ordered stream of events, and the Cosmos DB guarantees in order delivery of events within a logical partition. Now, let me start with a simple story to explain event sourcing. A few days ago, I decided to change my mobile phone. My current phone had a lot of issues, so I thought it was time to upgrade. I was looking for something good value for money, so I noticed this Pixel phone had some nice discount. So I went ahead to Google Store and chose a Pixel 9a. I selected the color, I selected the storage option, and then I clicked on Add to Cart. Now, if we think about this from a traditional relational database perspective, what would happen? Behind the scenes, the system would insert a row into the cards table containing the phone detail, right? Right after I added the phone to the cart, something interesting happened. A suggestion screen popped up, and one of the suggestion was a charger, since nowadays phone don't always comes with one. So I decided to add the charger to my cart. In the traditional model, this would simply create another row in the cart. But then I changed my mind. I realized I already had a charger at home, so I removed it from the cart. This would simply delete that row from the table. Now, if you look at the final state of the cards table, we would only see one item in the cart, that is the phone. But something interesting happened here, right? We actually lost a lot of information about what user did. Now let's take a look at the same scenario using event sourcing. Again, I go to the Google Store, choose Pixel 9a, select the color, select the storage, and add the item to the cart. Instead of updating a table, system records an event. Phone added to the cart would be the event, along with the metadata about the product. Next, as before, the suggestion screen appears. This action is also recorded as an event. Suggestion has been shown. And then I added charges to the card. The system records another event, that items added to the card along with the metadata. And when I decided to uh, remove that item from the card, there was another event that is added to the event store instead of deleting the data. And now if we look at the event store, something very interesting appears. We can see the entire sequence of action happen over the time. We have a complete history of user behavior, something that traditional database design completely lost. But the real power of event sourcing is not just storing the history. The real power comes from something called as projections. From the same event stream, we can build different read models for different teams. For example, the card service can build a projection to show the current card state. The recommendation team or the suggestion team can analyze what users had and remove over the time. The analytical team can study the user behavior patterns. And because we store the full sequence of events, we can even replay from the beginning. This allows us essentially to time travel back in time and reconstruct the past states and run different scenarios. Now that we understand the concept of event sourcing, let's take a look at how we actually implemented this pattern using Azure Cosmos DB. The first thing to look at is how we design our Cosmos DB container. In this implementation, we store three different document types within the same container, and that is one of the advantage of the Cosmos DB, right? The first type is the event document itself. These documents represent the actual event that occurs in the system. From a domain-driven design perspective, each event belongs to an aggregate. In our fraud detection system, one of the aggregate we use is the transaction aggregate, which represents the payment transaction. The second document type is aggregate document. And this document is extremely important because it stores the metadata about the aggregate, including the current stream version. Having this metadata helps us avoid unnecessary reads when writing events and improve the efficiency of event sourcing workflow. And the final document type that we have is snapshot document. Over time, an aggregate might accumulate hundreds or even thousands of events. And replaying all those events every time we load an aggregate can become very expensive. So after a certain threshold, we can create a snapshot which represent the state of the aggregate at that moment. The next time we load the aggregate, we start from the snapshot and replay only the remaining events. The partition strategy that we choose is the aggregation ID. So this has high cardinality, it distributes reads and writes evenly, and it keeps all the events for a given aggregate in the same logical partition, which is very important for transactions and ordering. And this is what an event document looks like. One important field to note here is the event schema version, which we will see in detail. Over the time, event payloads may evolve as the system changes. Having a schema version allow us to handle event schema evolution safely. Now let's take a look at how we handle concurrency using optimistic locking in Cosmos DB. The first thing is we read the aggregate metadata, we get the current stream version, capture the E tag, and we build the event. And then um, with the transaction batch, we create the events and also update the aggregate metadata. So when we replace the aggregate data with the E tag condition, the update only succeeds if no other process has modified the aggregate, right? So finally, we execute the batch, ensuring the operation is atomic within that particular partition. This is what our transaction aggregate looks like. The aggregate contains apply methods for each of the event types that we have. This keeps the domain logic encapsulated inside the aggregate. Now let's see how we load an aggregate from the event store. First, we check the snapshot, whether it exists or not. If it exists, we load it, and then we retrieve only the events that occurred after the snapshot. And if it doesn't, like, we will load all the events from the event store. Finally, we rehydrate the aggregate by applying those events. This process reconstructs the current state of the aggregate. Event schema evolution. During deserialization, we use this version, event schema version that we seen earlier in the event document, to determine how to interpret older event formats. This technique is called event upcasting, and it allows the system to evolve without breaking existing events. We also implemented idempotency checks. In our system, events may arrive through Azure Service Bus, especially when building projections. Idempotency ensure that even if the same message is processed multiple times, the system will not apply the event more than once. This is just a defensive check that you could have in your layer. Finally, we have this fraud detection approach where we have two-tier model. One, as I said before, we have the traditional machine learning model. Most transactions are evaluated using this model, which handle majority of the cases efficiently. When the ML model identifies the gray area or certain uncertain cases, we escalate those transactions to agentic AI. The agent can reason over additional signals and make more complex decisions. Now, let's take a look at the final demo of our application. Now, I'm going to start the simulation, and what is going to happen is there are multiple services involved in this particular flow: transaction service, device service, account service, and payment service. And I do have a simulator service which is going to pump hundreds of events per second into all these different services. And in the transaction service, as we have seen earlier, we have implemented the event sourcing pattern. And from there, the events are going to be published and going to create projections in the form of materialized view for our fraud detection agents to take into account and work on the evaluation based on it. And let me go ahead and start the simulation. So now you could see as the events are pumped into our system, via the server side events, the right side pane is getting updated. So the first one is the Cosmos DB container. It's going to be showing the events getting updated in all those different services. The next one is the projections that we have here, and the final one is the AA agents, the response that we got from the AA agents. Thank you for joining my session today. I hope this gave you some useful insights into building event sourcing with Azure Cosmos DB. If you have any questions or would like to connect with me, please feel free to reach out at this LinkedIn handle.